600 kilometers per second. That is the speed at which 100,000 galaxies, including our own, are hurtling toward something we cannot see. Science still cannot explain what it is, but that is only the first signal. There are 3 more, and the connection between them changes everything. Astronomers measuring galaxy motion expect uniform expansion, as the Big Bang predicts. They find the opposite: hundreds of galaxies flowing toward a single point no telescope can see. They call it the Great Attractor. The problem, it sits behind the zone of avoidance. The disk of our own galaxy blocks the view. The Milky Way's dust, its gas, its billions of stars form a wall. Imagine standing in a room with no windows, trying to describe what is outside by listening to the wind. Decades pass. X-ray and infrared telescopes, Rosat, Chandra, pierce through the dust. The Great Attractor is the Norma supercluster, a mass equivalent to tens of thousands of Milky Ways. That explains part of the motion, but not all of it. The Norma supercluster itself is moving toward the Shapley supercluster. And Shapley may be moving toward something beyond that, the Vela supercluster. The chain of gravitational anomalies extends past the edge of our maps. We have not finished measuring it. We do not fully understand it. And this is only the most local signal. The next one comes from the edge of the observable universe. NASA's WMAP satellite maps the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang, released 380,000 years after the beginning. For 13.8 billion years, that light has traveled through the space, carrying the imprint of creation. Cosmologists expect it to be almost perfectly uniform, tiny fluctuations of thousandths of a degree, the seeds of future galaxies. This is the foundation of lambda CDM, the standard model of cosmology. The model was built to explain these fluctuations. It works, except here. WMAP finds a hole 1.8 billion light-years across, one of the largest structures ever discovered. Too cold, 70 microkelvin below what any model predicts, and some measurements push to 140. The average CMB variation across the entire sky is 18 microkelvin. This deviates by several times that. Probability of occurring by chance, roughly 2%, 1 in 50. The leading explanation is a supervoid, a region with abnormally low matter density. CMB photons lose energy crossing it. They cool. What we see is the shadow of an immense, nearly empty region, and astronomers found a void there, the Eridanus supervoid. It is real. It is large. But according to Istvan Sapudi's 2015 study at the University of Hawaii, that void explains roughly half the anomaly. Half. The other half is completely unaccounted for after 2 decades. After WMAP confirmed it. After Planck, a far more sensitive satellite, confirmed it again. After every alternative explanation was tested and discarded. Half. And in 2017, researchers at Durham University published in monthly notices of the Royal Astronomical Society that the cold spot could be the imprint of a collision between our universe and another, a neighboring bubble in a multiverse. Not fringe speculation, a flagship astronomy journal, mathematically consistent with eternal inflation, but impossible to test. The cold spot remains unexplained, and the science has no answer. Alexander Kashlinsky at NASA's Goddard Space Flight Center studies galaxy clusters billions of light-years away. Not nearby clusters, clusters so distant their light left when the universe was half its current age. He uses the Sunyaev-Zeldovich effect. CMB photons pass through a cluster, and scatter off the hot electrons in the intracluster gas. The electrons impart a tiny energy shift. Measure that shift, and you know the cluster's motion relative to the CMB rest frame. It is extraordinarily subtle, but it works. Kashlinski expects random motion, local variations, the cosmological principle. The foundation of every modern cosmological model demands that the universe is the same in every direction at large scales. No preferred axis, no cosmic north. He finds a current, hundreds of galaxy clusters spread across billions of light years, across disconnected regions of the sky that have never been in causal contact, all moving in the same direction. At roughly 1,000 kilometers per second, he calls it dark flow, statistical significance 99%. Then Planck arrives, 10 times more sensitive than WMAP, and the picture fractures. Some Planck analyses detect the flow, others, using different cluster catalogues and different methodologies, do not. The Planck collaboration itself divides. Later studies have struggled to reproduce the signal, and the debate remains unresolved. Kashlinski and his collaborators continue to refine their methods, but the wider cosmological community has not reached consensus. If dark flow is real, the cosmological principle is wrong, and even if it is not, the very fact that the data can be read both ways tells you something. The model is not as solid as we thought. This is the most statistically robust signal of the four. The universe expands. At what speed? Two independent ways to measure it. Method 1, the CMB. Apply lambda CDM to the most precise map of the early universe ever made, Planck's data. Result, 67.4 kilometers per second per megaparsec. Uncertainty, just 0.5. Precision, better than 1%. Method 2, the cosmic distance ladder. Parallax measurements of nearby stars, Cepheid variable stars to calibrate distances tens of millions of light years out. Type 1, supernovae, exploding stars with known peak brightness, to reach billions of light years. Measure recession velocities. Result, 73.0. Uncertainty, 1.0. The difference is 5.6 units. The error bars do not overlap at all, 4 standard deviations apart. In physics, that is not an anomaly, it is a contradiction. 2 possibilities. One measurement has a systematic error that thousands of researchers across decades have failed to find, or the model is wrong. Then in 2025, the DESI collaboration releases data from its first 3 years mapping millions of galaxies. DESI finds that dark energy, the force driving accelerated expansion, may not be constant, it may be evolving, weakening across cosmic time. If true, the Hubble constant is not a constant. And lambda CDM and the pillar of cosmology for 25 years may need revision at its foundation. 4 signals, 4 cracks in the same foundation. For decades, cosmologists treated them as separate. The great attractor is local cartography. The cold spot is a statistical fluke. Dark flow is a measurement artifact. The Hubble tension is a systematic error. 4 isolated mysteries, 4 independent headaches. But what if they are not separate? Imagine the observable universe, our 93 billion light-year bubble, everything we can ever see, is not representative of the total universe, that beyond our cosmic horizon, beyond the reach of any photon that will ever reach us, there exist structures so vast their gravitational influence leaks into what we can observe. A structure of that scale would pull on everything within range. The Norma supercluster, the Shapley supercluster, our galaxy. It would explain the Great Attractor not as an isolated object, but as the innermost ripple of something far larger. That same gravitational shadow would create a dark flow across clusters that share no causal connection in the observable universe, but share a common external influence. It would imprint a cold spot on the CMB, not from a local void, but from a global asymmetry in the distribution of matter and energy beyond the horizon. And it would break the cosmological principle. If the universe is not homogeneous at the largest scales, the Hubble constant, measured from the CMB, assuming homogeneity, would diverge from the local measurement. Both would be right. They would be measuring different regions of a universe that is not the same everywhere. This is not established theory. It is a hypothesis that a handful of cosmologists are beginning to explore. 20 years ago, it would have been dismissed as absurd. Today, it sits at the edge of the data, waiting. Every telescope we launch finds something we did not expect. Hubble showed us an older universe. James Webb found galaxies that formed too early. Planck revealed cracks no one has closed. The Roman Space Telescope launches in months. It sees 100 times more sky than Hubble in one image. If the pattern holds, and it has never failed, it will find something we cannot explain, and the model will crack wider. The universe does not owe us an explanation, but it is giving us one anyway. We just do not know how to read it yet. 4 signals, one direction. Which do you find most difficult to explain? The Great Attractor, the cold spot, dark flow, the Hubble tension? Drop it in the comments. I read every answer. Subscribe to Untold Universe, Tuesday, Thursday, Saturday.